All right, we're back and hopefully a much shorter video this time. We're talking about LeChatelier's principle. And last video, we looked at concentration. This time, we're going to look at how changing the temperature can shift an equilibrium one direction or the other. Before we get into the problems here, I think it's important to note that there are really two types of reactions that exist out there. Let's say we've got A goes to B. Well, in almost every reaction I can think of, you either release heat during the reaction or heat is needed in order for the reaction to happen. Those two possibilities. So let's say in this particular reaction, heat is produced. We treat it like it's a product. We can even write it within the equation. This is what's known as an exothermic reaction. Exothermic, just suggesting that heat is given off by the reaction. It's a reaction that feels hot. On the other hand, it's possible to have a reaction that is very different. Let's say we have Y goes to form Z, right? But this time, in order for Y to turn into Z, it needs some heat. And so I'm going to write heat on the left side or on the reactant side. Anytime heat is needed for a reaction to occur, that's what we would refer to as an endothermic reaction. And it would actually feel cold to us. If you grabbed a container where this reaction were taking place, the heat from your hand would be taken away as it went into the reaction. And so you feel cold because heat's taken away from you. So in the reactions that I have set up below, or it's actually the same reaction, heat is a product. So we know that this is an exothermic reaction. And I want to do the second one first, okay? What we're going to do is we're going to treat heat just like it was any product or reactant of any other reaction. And in the second one down here, they ask, using the same reaction, which way will the equilibrium shift if heat is removed? That is, the temperature goes down. So we lower the temperature. And if we wanted to, we could draw a stress arrow where something looks like that, right? Now, imagine heat is, in this particular case, totally taken away. It's an unrealistic statement, but let's just pretend we remove all heat from the system. Well, like we asked before in the concentration video, which reaction cannot occur if all of the heat is removed? If all of the heat is removed, then the reverse reaction can't happen because SO3 needs that heat in order to break down and form reactants again, SO2 and O2. And so the question is, which reaction is favored, and what does that mean about the shift of the reaction? So we took away all of the heat. That means the reverse reaction can't happen. So the forward reaction must be happening, okay? And in order for that forward reaction to happen, that means the amount of SO2 must go down and the amount of O2 must go down. They have to react. And so they're going to disappear from the reaction and we're going to produce more SO3. So which way does the equilibrium shift? It shifts to the right as we produce more SO3. This is very different, by the way, than the concentration one, because in this case, the SO3 increases, the O2 goes down, the SO2 goes down. Every concentration changes in a measurable way, and there's no, the balance has changed, so to speak, in a profound way. And we're going to see that that actually has an impact on equilibrium constants, and we'll see that in a minute. Let's look at the first one, though. The first one says, which way will the equilibrium shift if the temperature goes up? Okay, well, if I have more heat, if that is my stress, then that means that SO3 is going to feed on that heat and use that heat to break down. That's going to drop the temperature back down a little bit. I should have um, I should have drawn an up arrow here in the first reaction too. The heat would increase over time. SO3 is going to react. It's going to decompose into SO2 and O2. If you're confused right now, the biggest thing that I can tell you is always look for the opposite to happen. If we're going to remove heat, the system is going to produce more of it. If we're going to increase the heat, the system is going to try to get rid of it. Okay? It is always opposite of whatever stress you put on the system. So let's look at one more thing. Different kind of question here. It says, which way would the equilibrium shift if heat was removed in this reaction? And then what would that do to the value of K? Well, remember, K is products over reactants. And if everything's a gas, which it is here, and HCl is on top, and H2 and Cl2 are on the bottom, let's first take a look at what happens if I remove heat. Okay, very similar to the scenario we saw in the second equation on the previous slide. I remove heat. Okay, the reverse reaction can't happen, so the forward reaction occurs. It's going to make the amount of HCl increase. Heat's going to go back up, always opposite, right? And the amount of Cl2 and H2 are going to go down to produce those products. Well, if we're saying, let's change the color here. If we're saying that HCl is going to get bigger and H2 is going to get smaller and Cl2 is going to get smaller, then that actually does change my constant. My constant is no longer a constant. So this is actually the one time that we've got to be aware that when we change temperature, we actually change the equilibrium constant, not just the position of equilibrium, but we change the value of the constant. And so what would happen in this case? Well, if my numerator is getting bigger and my denominator is getting smaller, then my value of K is getting much, much bigger, right? Now, let's look at the opposite scenario, the reaction on the bottom. Which way would the equilibrium shift if heat was removed? Let's do it again. If I remove heat in this endothermic reaction, then the forward reaction can't happen. So the reverse reaction is going to occur. That means NO2 is going to react. It's going to form N2O4. It's going to cause the amount of heat to go back up a little bit, not to where it was, but it'll go back up. And N2O4 will increase. Now think about our K value. K is equal to NO2 over N2O4. What did we just do to N2O4? We made N2O4. We made N2O4 bigger. And we made this smaller. So this is going to be small, numerator, denominator big. What happens to my value of K? It's getting smaller. It's getting smaller. Okay, let's come back to the Google Meet and we'll chat a little bit.